Okay, I want you to try a little experiment with me. Picture the word dolphin. Got it.
Yep, got it. I'm seeing fins, blowholes, the ocean.
Right. Now picture the word whale.
Okay, same ballpark. They're cousins, marine mammals. I get it.
Exactly. To you and me, those words are obviously related. They feel close. Now wipe that. Picture dolphin again.
Okay.
And now picture spaghetti.
Totally different vibe. I mean, unless you're having a very weird dinner.
Right. But here is the fundamental problem, the thing that, drove computer scientists up the wall for decades. To a computer, the word dolphin is just a string of letters, D-O-L-P-H-I-N.
Sure.
The word whale is 5 letters. Spaghetti is 9. To a machine, dolphin is just as unrelated to whale as it is to spaghetti.
They're just arbitrary symbols. There is no ocean baked into the letters D-O-L-P-H-I-N.
Exactly. It's the classic symbol grounding problem, right?
Yeah.
The computer has to label the word, but it has absolutely no idea what that label is attached to in the real world.
To the machine, it's all just noise.
And yet, if I go to an AI chat today and type in dolphin, it knows it's an animal. It knows it swims. It knows it's not pasta. So the billion-dollar question is, how did we bridge that gap?
How did we teach a rock, which is basically what a computer chip is, to understand the meaning of a word?
That is exactly the mission of today's deep dive.
Yeah, we are stripping away the magic and looking at something called word representation. Specifically, how we turn these symbols into math, into vectors that let a computer measure meaning.
And to guide us, we are looking at a really foundational text, Chapter 14, Word Representation by Omer Levy. It's a dense read. I mean, it's packed with linear algebra, but it tells this incredible story.
It really is the bridge. It connects the, pen and paper linguists of the 1950s to the massive data centers we have today.
So let's start with the intuition. If we can't give the computer a dictionary definition, because, it doesn't understand the words in the definition either, where do we even begin?
We begin with something called the distributional hypothesis.
Which sounds very academic.
It does, but the concept is beautifully simple. It goes back to a linguist named J.R. Firth in 1957, and he dropped this famous line that became, the golden rule of this field.
Okay.
He said, "You shall know a word by the company it keeps."
You shall know a word by the company it keeps.
I love that. It sounds like something a grandmother would warn you about.
That's literally the
Yeah.
mechanism. The idea is that a word's meaning isn't contained inside the word. It's defined by the words that surround it. The context is the definition.
Levy uses a fantastic example in the source material to prove this. He throws out a word, amba, A-M-B-A. Now, be honest, before reading this, did you know what amba was?
I actually did, but only because I'm a foodie. But for the sake of the experiment, let's just say it's a total mystery.
Right. To most people, amba is just a random symbol. It could be anything. But then the text gives us a sentence. Listen to this. "You should pour some amba on your falafel. It's delicious."
Okay, so let's play detective. What just happened in your brain right now? Well, pour is a dead giveaway. You pour liquids, you pour sauces. So amba is like a liquid. Falafel tells me we're in the realm of food, probably Middle Eastern cuisine. And delicious confirms it's something you eat, not, detergent.
Exactly. You just triangulated the meaning of amba purely by looking at its neighbors. Pour, falafel, delicious. You define the word by its environment.
So the computational approach is basically to do that detective work, but for every single word in the English language all at once.
That's it. We stop treating words as single symbols and start treating them as vectors.
Let's pause on vector. To anyone who isn't a math person, that word can trigger some high school trauma. What are we actually talking about?
Keep it simple. A vector is just a list of numbers. Imagine a giant spreadsheet. Every row in that spreadsheet is a word in the dictionary. Dolphin, spaghetti, amba.
Okay, I can picture that.
And every column is a potential context word.
So let's say we're building the vector for dolphin. We look at the dolphin row. We scan across to the column for the word ocean. Do they appear together often?
Yes, very frequently. So we put a high number in that cell. Then we check the column for swim.
Another high number.
Then we check the column for tomato.
Probably a 0. Or very, very close to it.
Right. So the dolphin vector is this long list of numbers. It has spikes for C words and flat lines for food words.
And spaghetti is the opposite. It has spikes for sauce, boil, Italy, and flat lines for ocean.
And this is where the magic happens. Once you have these lists of numbers, you can do math on them. If you take the dolphin list and the whale list and sort of overlay them, the spikes line up.
They overlap.
Yeah. Mathematically, we say they are close in vector space.
Whereas dolphin and spaghetti would have almost no overlap. Their vectors are pointing in totally different directions.
Exactly. The computer has never seen a dolphin, but it knows that the context distribution of the word dolphin is statistically almost identical to whale. Therefore, they must mean similar things.
That seems straightforward enough, but the source material really emphasizes that the word context is a tricky variable. We assume it just means the word next door, but Levy points out it's way more nuanced.
Oh, this is a crucial insight. The definition of context isn't fixed, and how you define it completely changes what the computer learns.
Give me an example. How does changing the context change the meaning?
Well, let's look at an older method, latent semantic analysis, or LSA. In LSA, the context isn't just the word next door, it's the entire document.
So if the word alien appears in a sci-fi novel, the context for that word is the whole book.
Yes, and when you use that wide lens, the computer learns topical similarity. It learns that alien and spaceship are related. They belong to the same topic.
But they aren't the same thing. I mean, an alien isn't a spaceship.
Correct. They're topically related, but not functionally similar. To get that kind of distinction, you need to zoom in. You use a window approach, just looking at, say, one or two words to the left and right.
Okay, so we're narrowing the scope now.
Right. And when the window is small, the computer learns attributional similarity. Think about dog and cat. Topically, they're both pets, but functionally, they appear in the exact same spots in a sentence.
I fed the dog, I fed the cat slept, the cat slept. Yeah, you can swap them.
You can swap them. You can't say, I fed the spaceship. So a small window teaches the computer that dogs and cats are the same type of thing. They share attributes.
That makes a lot of sense. The text also mentions something called syntactic dependencies as a context. It sounded like it was for the grammar nerds, but it seems really powerful.
It is. It solves a big problem.
Yeah.
Long-distance relationships between words.
Like when a sentence is really long and the relevant words are far apart.
Right. The source uses this great example. Australian scientists discover new planets with a revolutionary telescope.
Okay. Australian scientists discover new planets with a revolutionary telescope.
So if you just use a small window of neighbors, telescope is next to revolutionary, which is fine. It's a description, but it doesn't tell you what a telescope does.
But grammatically, telescope is connected to the verb discover. It's the instrument of discovery.
Exactly. Even though they're 5 words apart, the syntax links them. And if you use that grammatical link as your context, the computer learns these incredibly precise functional relationships. Telescopes are for discovering. Forks are for eating.
Wow, okay, there was one more context type I found fascinating. The symmetric pattern. The X and Y structure.
Oh, this is a clever hack. It solves the synonym versus antonym headache.
Right, because synonyms and antonyms look the same to a computer. Good and bad appear in the exact same spots. It was a good movie, it was a bad movie.
They're totally interchangeable in that sense. So a basic model thinks good means the same thing as bad, but you almost never see the phrase good and bad.
Or good or bad.
Exactly. But you do see knives and forks, or bat and ball, or neither scorpions nor spiders. These X and Y patterns signal that two things are distinct but belong to the same class. It helps the computer tease apart what's related from what's identical.
Okay, so we've built our spreadsheet. We have our words, we have our contexts. Now we have to fill in the numbers. And the, naive approach is just counting, right? Dog appears with the 5,000 times.
And just counting is a disaster.
Why? Because the appears with everything.
Exactly. If you just use raw counts, the word the becomes the most important feature of every single noun. It just washes out all the unique meaning. It's pure noise.
So how do we find the signal in that noise?
We use a metric called PMI, pointwise mutual information.
God, that sounds intense.
It's actually measuring something very intuitive. Surprise.
Surprise. How?
It asks a simple statistical question. How much more often do these two words appear together than I would expect by pure random chance?
Walk me through that.
We know the sova is everywhere. So seeing the next to dog is not surprising at all. The probability is high just by chance. So the PMI score is low. It basically says, boring. Ignore this.
But seeing amba next to falafel.
Amba is rare. Falafel is relatively rare. The odds of them just bumping into each other by accident are tiny. So when we do see them together, the PMI score skyrockets.
So it tells the computer, this is a meaningful connection. Pay attention.
It downweights the filler words and highlights the unique, meaningful pairings. Yes, but there's a catch.
There is always a catch with statistics.
PMI is a bit of a drama queen about rare events.
How so?
It has a mathematical bias toward low-frequency words. So if you have a typo or some weird creative sentence like, the zebra cooked a souffle, and that pair appears just once in the whole database, PMI goes crazy.
Because zebra and souffle are both so rare.
Right. The probability of them meeting was practically zero, so the fact that they met once makes PMI think they're soulmates, you know? It overvalues rare noise.
So how do we calm it down?
We use something called context distribution smoothing. That's the technical term. In simple English, we just artificially boost the counts of the rare contexts a little bit.
Like grading on a curve.
Essentially, yeah. We raise the probability to a power usually denoted as alpha, often around 0.75. It just dampens that surprise factor for the super rare stuff, so one weird sentence doesn't ruin the entire model.
Okay, so we've refined our numbers. We've got this huge matrix of words and their PMI scores. But we still have a size problem, right? The English language has hundreds of thousands of words.
Which means our spreadsheet is massive. If you have a column for every context word, your matrix is like 1,000,000 columns wide.
And most of it is empty. Dolphin doesn't appear with Constitution or asphalt.
Right, it's 99% zeros. We call this a sparse vector, and computationally, this is a nightmare. It's a huge waste of memory, and it's really hard to process. We want dense vectors.
We want to squash that 1,000,000-column spreadsheet down.
Exactly. We want to compress all that information into maybe 300 dimensions. We call these embeddings. The source details two main ways to do this. The first is SVD singular value decomposition.
Which is old school linear algebra.
It is. SVD looks at the whole spreadsheet and finds the underlying themes. It says, okay, you have columns for tire, brake, and steering wheel. I'm just going to squash those into one dimension called car parts.
So it simplifies the data without losing the core information.
Exactly. It creates the best low-rank approximation. It was the gold standard for years. But then came Word2Vec.
The celebrity of the NLP world.
Word2Vec took a totally different approach. Instead of doing big math on the whole spreadsheet at once, it used a learning algorithm, specifically something called negative sampling.
I loved this concept in the reading. It felt like the computer was playing a game of hot or cold.
That's a great analogy. The algorithm looks at a real sentence, dolphin swims in ocean. It wants to pull the vectors for dolphin and ocean closer together. That's the hot part.
Okay, and then it generates fake data.
It grabs random words from the dictionary. It says, okay, how about dolphin and bicycle? It assumes that's a negative pair because it didn't see it in the text.
So it pushes those vectors apart. That's the cold part.
Exactly. It's constantly tugging meaningful words closer and pushing random words away. And by doing that millions of times, you end up with these beautifully organized, dense vectors.
That's so clever.
And Livy makes a really interesting point here. Negative sampling is actually doing the same thing as the SVD matrix factorization, just from a different angle. They are mathematically linked.
So we've compressed the language. Now we have to talk about the most famous thing in this entire field, the king minus man equation.
The word analogy phenomenon.
This is the thing that makes people's jaws drop. You take the vector for king, you subtract the numbers for man, you add the numbers for woman, and the result is...
the vector for queen.
When this first came out, everyone, including me, thought, oh my God, the computer has understood the concept of gender. We imagined the vectors were like a map. If you walk 3 steps east, you go from male to female.
The offset interpretation. It implies there is a specific gender arrow in the vector space that you can just follow.
But Levy and Goldberg, who wrote our source, decided to actually check the math on that. And they found out that's not really what's happening.
Yeah, it's a bit of a buzzkill, but an important one. They show that the math behind king minus man plus woman isn't measuring a geometric distance or an offset. It's actually performing a specific type of similarity search.
So what is the equation really asking the computer to do?
It's balancing 3 things. It's looking for a word that is, 1, very similar to king, 2, very similar to woman, and 3...
very dissimilar to man.
Exactly. It's an additive search. It's asking, give me the royal female that is not the male.
And the answer to royal female not male is queen.
Right. It's not that the computer understands the abstract concept of a gender direction. It's that queen is the only word in the dictionary that shares the royal context of king and the female context of woman, but lacks the male context of man.
That's a subtle but really important distinction. It's about similarity, not geometry.
And another researcher mentioned in the text, Linson, pointed out that often the algorithm is actually pretty lazy.
Lazy how?
Sometimes king minus man plus woman equals queen, just because queen is the closest neighbor to king that isn't king itself.
So it's just looking for the next best thing in the neighborhood.
Often, yeah. It's sophisticated pattern matching, not philosophical understanding.
Which brings us to the big so what? We've gone from counting words to building these dense, complex vectors. Why does this matter? Why is this the foundation of modern AI?
One word: generalization.
Explain that.
In the old days, if I taught a spam filter to block the word buy and a spammer used the word purchase, the filter failed.
Because to the computer, buy and purchase were totally different symbols.
Exactly. DOLPHIN versus WHALE all over again. But with these vectors, buy and purchase have almost identical lists of numbers. They live in the same mathematical neighborhood.
Oh, okay.
So if I train a neural network on buy, it automatically works for purchase.
Transfers the knowledge.
Exactly. That is the superpower of deep learning. You don't have to teach it every single variation. The vectors provide a kind of pre-baked understanding of how words relate to each other.
It's like giving the AI a massive head start.
A massive head start. It essentially allows the computer to use common sense that it derived from reading billions of sentences.
Before we wrap up, I want to leave the listeners with a problem that the text hints at. We've been talking about a vector for a word, one-to-one.
Right. One row in the spreadsheet for each word.
But what about the word bank? You can deposit money in a bank, or you can sit on a riverbank.
The problem of polysemy. Multiple meanings.
So in the models we discussed today, bank gets just one vector. So what does that vector even look like? Is it a money vector or a river vector?
It's a mashup. It's an average of both meanings, which means it's actually not very good at being either one. It's a blurry vector. It's sort of half financial, half muddy.
And that seems like a fatal flaw if we want computers to really understand us.
It was. And that's where the field has gone since this text was written. We've moved from word representations to contextualized embeddings.
Meaning the vector for a word actually changes depending on the sentence it's in.
Exactly. In modern systems, like the ones that power the big AI models today, the vector for bank is calculated live based on the words around it. If the sentence says, "I fished at the bank," the model generates a river vector on the fly.
So we're looping right back to the very beginning. You shall know a word by the company it keeps. But now we're judging that company in real time every single time the word is used.
Precisely. The distributional hypothesis is still the engine, but that engine is getting much, much smarter at handling the nuance of language.
It is wild to think that all of this, Siri, Translate, all the chatbots, it all starts with simply counting which words hang out together.
It's the simple power of statistics applied to the messy beauty of language.
Well, next time you're typing into a chatbot, remember, it's not reading your mind. It's doing high-speed vector calculus on the company your words keep.
It's the most impressive math trick in history.
Thanks for listening to this deep dive on word representation. We'll catch you on the next one.